Hello, welcome. In the last course, we talked about using neural networks to parameterize unknown functions in the function inverse problem. And the next lecture will tell you something about the basics of training methods for this kind of PDE constraint optimization with neural networks embedded in it. And the idea is to go back to computational graph. And we already talked about how numerical solvers can be expressed by a computational graph. And as you already know, the neural networks can also be expressed by a computational graph. So the key idea is how to combine these two computational graphs. For example, for the neural network computational graph, you parameterize your kappa x function, where the input is x and the output is kappa theta x, where theta is the weights and the basis, which is w and b. You can view w as a vector of all weights and b as a vector of all bases. And you want to the output of a kappa theta to be the input of the numerical solver. And then you do some numerical solving steps and you get the observation. And this is the independent case where your kappa x does not depend on the state variables. And in a more complicated case, your kappa x also your kappa also depends on u, which is the state variable. And then you have to loop over these two neural networks and numerical solver computational graph, or even you have to merge these two computational graph that can be very complex eventually. But in this course, we will focus on how this works for the case where kappa only depends on x instead of depending on u and x simultaneously. And the first step is to discretize the PDE system, where we have the PDE constraint optimization problem here, and we can discretize each term. And in the next lecture, we already talked about how to represent the discretized system of the PDE using this formula, which is a linear system, where each step you have to solve a linear system. And the objective function is also discretized. And in this case, we just use a simple integration rule. We just use the nodal values at k minus 1 delta t and sum up all the discrepancies as an approximation to the integral value. And so this is the discretized optimization problem. And then you draw the computational graph for the forward computation, where you have a lot of for each blue box, for each green box, you have all the u vectors, and and here you need the first vector, the first value, the leftmost temperature. So that comes out of the first node, and you assemble all the temperature on the left-hand side, and then you formulate the loss function. And this is where theta comes in. For each step, when you go from u1 to u2, and to computing u2, you have to use theta to compute u2. So this known vector takes u1 as input and also takes theta as input, and then compute u2, and then it is similar for u3 and u4 and until the next step. Then we can just do automatic differentiation on this computational graph. You just backpropagate your gradient from next output to theta. Let's see how we can do that in the next few lectures.